Well, good morning and good afternoon to everyone, and thank you for joining us for this webinar. We're excited to be able to share some information about retaining wall systems in highway works with you today. Again, this is Ryan Berg. I'll be leading off the presentation, and again, that'll be followed with presentations by Jim and Daniel. I'm going to talk about applications of these wall systems. Jim will talk about design, and Daniel will talk about the idea evaluation program for retaining wall systems. We're going to focus today on large precast block wall systems used both in gravity wall systems and in MSE, mechanically stabilized earth wall systems. And we will be focusing on applications in transportation works. Again, any questions, please type those into the comment box and we will address those, the three presenters at the end of the presentation here. I'm a consultant in St. Paul, Minnesota. I do quite a bit of work with the Minnesota Department of Transportation. And from an application standpoint, I'm going to share with you what MnDOT and the precast industry have developed and worked on starting about 10 years ago on the applications of these walls within MnDOT and within the state of Minnesota. Again, I'm a consultant to MnDOT, work closely with the MnDOT Bridge Office and with the Foundations Office on this program. The nomenclature we're going to use, the MnDOT shows up here, and then these large block walls in MnDOT nomenclature, we call them precast modular block walls. So PMBWs. And what we're talking about is shown here. This is a shot of the back side of a retaining wall under construction. And our standard or our typical dry cast blocks, our keystone anchor wall type blocks, those are typically 16 inches wide, 8 inches in height, and 12 inches front to back. This particular wet cast PMBW unit is 46 inches wide, 18 inches high, and 28 inches deep front to back. So these wet cast units that we're going to be talking about today, so very large units, and we'll take an example of some of these different types of units. They can be solid units like we see here. They can be more panel type like units. They can vary from 18 to 48 inches high and from 48 inches to 96 inches long. This is going to be an MSE structure. It has geogrid cast into these units. This is a bin type of unit, precast unit with gravity wall construction, and this is a bin type or double T type unit used with an MSE construction technique here. So there's a variety of units. They have a variety of heights, variety of configurations. So the challenge to both the industry and to MnDOT is how do you write standards and utilize these products on highway works when they come in such a variation in sizes. So why do we want to use these? Why does MnDOT want to use these? What sort of technical guidance did MnDOT develop, again, in concert with the precast industry? And specifically, what type of guidance did they develop for gravity wall applications and then also for MSE applications? Well, why do we use these? First of all, it's aesthetics. As you saw in some of these photos here, although these were under construction, form liners are used with these large wet cast blocks. Therefore, you can get stone-like finishes, a variety of stone-like finishes on the front. And once they're in place and they're stained, they look like rock structures. So they're very attractive from an aesthetic standpoint. They can be used to fit into historical areas and so forth, or to match other types of cast in place structures. Another reason to use these, and this is particularly evident in Minnesota with our use of de-icing salts in the winter, is that the air entrained wet cast units are very durable. So they're very durable, very resistant to deterioration from the de-icing salts. And from a agency standpoint, we want to use these because there are a variety of suppliers within the state. So we've got good competition, so that's something we should be using in our highway works. The gravity walls, they're attractive to use because the design is fairly straightforward. Construction is fairly quick. These large units go up very quickly as they're unloaded and stacked and backfilled. And if it was just this Minnesota DOT themselves using the products, that would be kind of a limited market. But of course, what we see is that once MnDOT develops standards of practice for these systems, including approved product lists, then we see a larger use of these products, these wall systems on state aid projects. That is, projects, roadway projects that counties and or municipalities would design and construct. Likewise, we see broader use just by the general civil engineering community itself that can rely on the MnDOT standards for these different retaining wall systems. So a lot of positive reasons to use these wall systems, and particularly the gravity walls. Well, why use them for MSE walls? A typical MSE wall would have a thin 6-inch thick or 5.5-inch thick panel facing. How can we put this much concrete in the front of an MSE wall and be competitive or be practical? We're not really envisioning that we're going to replace panel MSE wall structures in highway works. However, we do see a variety of projects where gravity walls and the aesthetics are very attractive to use a PMBW, but in some sections of that project, the walls are so tall that gravity does not get us there. So an MSE combination in those sections provide a nice, clean project and gives the designers a lot of options. And in the future, we hope that design procedures are refined, and Jim's actually going to talk about this a little bit, to address the stability that the large block facings provide in the front of an MSE wall. So to add that component into the design to reduce the amount of reinforcement, whether it's the number of layers of soil reinforcement or the length of soil reinforcement. And this is further illustrated here. This is a earth retaining, a chart of different types of earth retention structures, fill type of construction from work by paper by O'Rourke and Jones in 1990. And this is something I modified in 2010, and specifically would call an MSE wall with large face units really a hybrid type of wall. If we can incorporate the stability effects of that gravity wall, that large block, with MSE, we can design it as a hybrid wall and pick up some additional efficiencies and economies. Another type of combination we may have is illustrated here, where the lower portion of the wall is an MSE wall and the upper portion of the wall is a gravity wall. So if we can come up and develop design procedures to design like this, the benefit of this is just giving us more space up on top of the wall where there's no geogrid reinforcement, for more room for pavement structures, drainage structures, traffic barrier, reaction slabs, and so forth. So this is another type of hybrid wall we certainly envision on being used. The gravity walls, again, are very attractive. This is just a typical cross section of a gravity wall. And where these systems get used in roadway projects, I've got a few examples here. This is a road widening project in South St. Paul. And in this case, the road widening took back the earth slope that was in front of this house, took it back to the right of way. And here we see a gravity wall with a coping cast in on top of it and stained to make it look like a limestone rock wall. Here's another application of just a bus stop at a park and ride, just a short gravity wall separating the bus pickup from the parking lot. Here's another application, and this is between St. Paul and Minneapolis. The Interstate 94 is depressed in several locations, so there are slopes coming down to the freeway. And after the I-35W bridge collapse, they took the shoulders and made those traffic lanes to accommodate the traffic with the 35W out of service. Afterwards, of course, people wanted to keep those shoulders as traveling lanes. So what MnDOT came up with was leaving those lanes in place, and instead of shoulders, they created emergency pull-off areas. You can see here by constructing large block walls into the cutting into the slope, constructing large block walls, and developing paved pull-off areas for emergencies in this depressed roadway section. They also found along I-94 that this is a good practice to create construction working space, in this case a new overhead sign system. So they developed a work area by installing a retaining wall, and also end up with another emergency pull-off area behind that wall structure, behind that sign structure. So from an application standpoint, some of the challenges the agency found were how do you address the different types of walls and the different types of suppliers, these different blocks. One system may have maybe 2 or 3 block depths. Another system may have a much greater variety of wall depths, and with that, they're able to design and construct taller gravity walls. So from an agency standpoint, how do you come up with a competitive environment for different wall systems and something that the agency is comfortable using? And again, MnDOT worked with the precast industry, with suppliers in the states, and for gravity walls, they came up with a comfort level of gravity walls being used up to 8 feet in height. And that allowed the use of a variety of systems. And they called that phase 1. And here's a typical section detail from MnDOT. Of course, we've got a lot of frost depth down here, so we got a 4-foot depth. The walls need to go down to on the bottom of a leveling pad. And we go up to a maximum of 8 foot in height from the top of leveling pad to the top of the retaining wall. From a drainage standpoint and from a construction standpoint, we do call for a 12-inch drain zone of aggregate immediately behind the blocks. Again, that can pick up any water that's coming through the soil, but it also provides good compaction, fills in the zone, the triangular zones in between adjacent blocks. And we see here at the footing that we can go from 6 inches to 2 feet in the thickness of the footing here. Well, why? That seems kind of odd. Why did we do that? Well, remember, these blocks come in different heights. The wall is set by the top of wall. The bottom of the wall can be variable. So by allowing a 6 inch to 24 inch thickness of leveling pad, that allows different height blocks to competitively bid on these different projects. And if 2 feet is more than somebody wants to put in, they can go to a 6-inch minimum concrete leveling pad on top of 6 to 24 inches of a wrapped coarse filter aggregate. Again, this is just on the gravity walls. So that's how they classified and use gravity PMBWs. And then with MSE walls, they have 2 additional phases or application areas. The first is MSE walls up to 12 foot in height. And that is really for new systems that haven't been used by MnDOT before. So that they'll build a couple of projects, everybody feel good about it. They'll measure it, face rotation and so forth during construction. And once the comfort level is up with that system, that can go up to 20 feet in height, but that 20 foot in height also requires a detailed submittal from the vendor of a review of their system by a national expert. And that's where we'll get into this idea program that Daniel will talk about. So here's a typical MSE wall. Again, 4 foot embedment depth, 1 foot drainage zone behind the block units. And here's some of the different systems that may work with the with geogrids, which are typically used for the MSE construction. Now here's a couple of application of MSE block walls. And this one's actually a combination of gravity walls in the lower heights of the structure with MSE walls in the taller portions of the structure. And this is a pedestrian underpass of a roadway out in western Minnesota. So here's a good application where the local agency liked the aesthetics of this type of wall system, and economically there was a lot of gravity system, and MSE was just needed in a couple of areas for the taller wall systems. These are also popular for side hill fills or cuts along the freeway. Here's a couple of them along I-694 along the northern portion of St. Paul, Minneapolis. So these are some typical applications we see today. Here's an application on a county road. So this was a county project. We're looking at construction. In this case, we see the 1 foot, maybe greater than 1 foot zone of stone immediately behind the units. Again, the stone's used to fill in this zone in between the blocks. A geotextile filter between the sand fill and the stone. And this particular system used a geogrid connection between the blocks that had 2 tails of geogrid. So this is the lower tail stretched out here, and the upper tails folded over until the next soil layers are placed. Some of the issues that were faced by the agency to develop standard specifications and details for these were the implementation of the systems, working with the industry, some of the design aspects of how to design the gravity walls, the MSE walls, and then detailing aspects. Again, we needed to address where was the cutoff point between gravity and MSE walls. Again, that was landed at 8 foot height. Need to develop standard specifications for both. Need to be able to address the various height units that are in the industry and how we can utilize all of those. And a particular concern with MnDOT was the wall system design. So this is something where we're going to specify top of wall, bottom of wall, and the supplier, the contractor, supplies the materials, whether it's just the block with the gravity wall and the design, or if it's an MSE wall, it's the block, the geogrid, and the design. And MnDOT wanted to specifically know what systems we're going to use, what engineers. So a supplier could list 2 or 3 engineers, and they're part of the pre-qualification list or the approved product list, and they have to be used on a project, or a new engineer has to be approved. So special provisions were developed, approved product lists were developed, and review processes were developed for putting these systems on these approved product lists. Design issues, again, was part of the implementation issues, addressing the various height units, the design engineer, and again, the detail on how a large block is incorporated in MSE wall design. How do you factor in the contribution of that large block? Detailing, I've talked about the unit heights before. But the other detailing issues with these blocks, and again, they come in various lengths, is how do you develop top of wall coping? How do you develop traffic barriers to go on top of these walls? And how do you even anchor fences on top of these walls when you're looking at a variety of blocks being used? And some of those issues are still being addressed by industry and being worked out by industry today. So we do not currently have a good generic traffic barrier detail for these various wall systems. Coping, here's a shot of that wall on County Road 42. The wall construction was fairly quick. The cast in place coping, that was quite a bit of handwork, carpentry work out there. So that turned out to be a fairly large cost component. So these issues of top of wall issues are something that continued refinement are being made. So in summary, MnDOT worked with industry. They developed special provisions for both gravity and MSE walls. They divided up applications into heights ranges where they can be applied. And really, this has been working very well for MnDOT and for the state aid projects for counties and for local municipalities utilizing these systems on their highway works, roadway works. A couple more notes. Currently, MnDOT is not allowing roadways to be supported on top of these walls, and that's basically because this traffic barrier detail has not been fully developed. I think on a project-specific basis with a specific wall block unit, something could be developed, but from a generic standpoint, we're not quite there yet. So that is a small limitation on keeping vehicle off of the gravity walls or off of the MSE walls. Again, the specifications and provisions were developed for use of gravity and MSE walls. These are all available at the MnDOT website. Approved supplier lists are listed on the MnDOT website as well. It looks like this. It'll give you the wall system, what phase they're approved to, the date they were pre-qualified. And as you get into some of the additional details, the engineering and so forth are detailed as well. And these are by different manufacturers as well. It's not just wall systems because the precasters themselves have to be pre-qualified. So that's a quick summary of practice in Minnesota and how these walls are becoming more popular. Any additional questions, you could contact Joe Black, who's a Bridge Office Standards Engineer, or myself. And with that, I will toss this over to Jim.
Thank you, Ryan. All right, can you see my screen? Hopefully.
Yes. Yes.
Hopefully, yes. Thank you. So Ryan did a great job kind of setting the stage for Daniel and I and my portions of the webinar. I'm going to go into design. Unfortunately, I think this is a little drier than what Ryan and Daniel are going to cover. Ryan has covered and Daniel will cover. But if you stay with me through the design and the equations, at the end I'll show or demonstrate the impact of the new design methodologies that we have with large blocks. I think that'll be hopefully worth the next 20 minutes. So I'm going to talk about design and specifically the AASHTO LRFD design specifications, the 2020 specifications that have come out. And then FHWA has authorized an update to the design and construction manual for MSE walls. I'm part of the team that's involved with that with Tom Taylor, Dr. Jihan, Dr. Ken Fishman, and Stan Boyle. And that manual is is to provide further guidance from the AASHTO, and it's currently complete and going through industry and FHWA review. And we hope that it'll be final and out for public use by the end of this year or early in 2022. So I want to start with a little bit of history of design methodologies, where we come from and where we are today. And the older I get, the more I like to talk about history, I guess. But at any rate, so if we go back to the beginning of modern day reinforced soil, Henry Vidal and the Reinforced Earth Company really set the stage. And back in the 1980s, and they developed their own design methodology called the coherent gravity method, which was designed specifically for metallic reinforcement. And they still use that method today. Many systems that use metallic reinforcement use that coherent gravity method. So that's been around since, like I said, the 1980s. In the 1990s, as this technology was being used more readily by the states, FHWA, and each of the systems that were available at that time had their own design methodology. So it was difficult to do an evaluation of the designs. So FHWA commissioned an extensive research program that culminated in the simplified design method. So this was a program that was spearheaded by Dr. Barry Christopher with a team of national, international experts. And they went through a process of about 4 or 5 years of doing lots of research and then actually constructing and instrumenting a series of MSE walls with different facing, different reinforcement types. And the basis of that was the development of the simplified method. And that was published in the MSE design and construction guidelines that Ryan, Barry Christopher, and Naresh Semtami were the lead authors in. So that's in the 90s. And then more recently, over the last decade, maybe 15 years, Tony Allen and Richard Bathurst have developed a simplified stiffness method. This is a method that has been developed exclusively so far for geosynthetic reinforced structures. And it's empirically based, and it's based on instrumented full-scale and laboratory tests. And then finally, the limited equilibrium method, which the version that we are using within AASHTO and GEC 11 was developed by Doug Lashinsky, and that came out in the last 5 to 10 years. Let's see, before I go on. So you'll see that I have inextensible and extensible reinforcements. Our inextensible are our steel reinforcements, extensible predominantly geosynthetics, and the coherent gravity is pretty much exclusively used for steel reinforcement. The simplified method can be used for either steel or geosynthetic. And then the last two, the simplified stiffness and the limited equilibrium, are currently for extensible reinforcements only. So terminology is always a little bit different. MnDOT has named the large block PMW, PMBW. We in the manual are using large block, and this is the first time in FHWA guidance that we're specifically addressing large modular block in the design manual. The AASHTO 2020, really there are no significant changes in gravity wall design in there. Ryan's touched on it in his presentation. I'm not going to discuss that any further in my presentation. I'm going to focus on MSE wall designs with large block using either the simplified stiffness or the limited equilibrium method. And before we get into the details, we want to just do a little review. So all of the methods that I'm going to talk about cover external stability, sliding, eccentricity, and bearing capacity in the same way. There's no difference in the methodology for those. It's the same earth pressure theory, bearing capacity. So there's no change for external stability. So that's really the last I'm going to talk about external stability in this portion of the presentation also. Now for internal stability, the load in the reinforcement is the key, and we want to make sure that the load in the reinforcement does not cause it to rupture, to pull out, or to have a failure at the connection. And each of the three methods that we're going to talk about determine that load, that T max, in a different way. And we'll see that that it has a significant impact on the design load that we will design for. For internal stability, we have this internal failure surface. There we go. We have an internal failure surface within our mass, and for extensible reinforcements, our geosynthetics, that failure surface is a Rankine failure surface where the soil reaches its full strength before failure. For our steel reinforcement, our inextensible, those are much stiffer, and so when failure occurs, we don't develop that full Rankine failure surface, and we get a bilinear failure surface. Again, for the designs we're going to talk about, we're going to be focusing certainly with the simplified method and the simplified stiffness method with this Rankine failure surface. So the first we're going to cover is the simplified method, and its name is pretty appropriate. It's a really simple approach to determine the internal stresses on each reinforcement layer. And so if we have a layer of reinforcement, we want to determine the T max of that layer. We're going to consider the vertical load on that reinforcement layer and multiply it by a earth pressure coefficient to determine the horizontal stresses. And that vertical load, using LRFD, we've got a vertical load factor, we've got our weight of the soil and weight of the surcharge above the soil, and then if we have a live load, we've got our live load load factor and our live load. So we can determine the vertical load. Once we know that, simplified method really is they've taken and for all the different reinforcement types, calibrated this earth pressure coefficient. And if we focus on the figure on the right here, so this is again empirically derived from that NCHRP work back in the late 80s, 90s. So for geosynthetic reinforced structures, the ratio of K to Ka is 1. So here for geosynthetics, we design for an active earth pressure. For our steel reinforcements that are stiffer and they create a stiffer soil mass, the earth pressure that we design for is a function of where in the wall we are at the top of the wall to a depth of 20 feet, and it's anywhere from 1.7 to 2.5 times that active earth pressure. So this is empirically how Barry and his group developed the simplified method to address all reinforcement types. So once we know what geosynthetic or reinforcement we're going to use, we can determine this K value and then determine our maximum load at any reinforcement level. And that's going to be the tributary area, the vertical spacing between reinforcements. But I wanted to include this figure because the earth pressure theory that we're going to use is a triangular, right? It increases with depth. And so the requirements for reinforcement in the bottom of a wall are going to be significantly higher than the requirements for the reinforcement of the upper portion of the wall. So for the simplified method, in summary, it has a 30-year track record, has proven to be safe and conservative designs, and I think we'll see many designers continue to use it. However, it provides no direct benefit for the added mass when using these large modular block wall units, something that Ryan talked about briefly. So it's really ignored in the simplified method. So now if we move to the simplified stiffness method, and it's really not, it's simplified a little bit, but it's nowhere close to as simple as this simplified method. So some of the keys are the Tmax distribution is no longer triangular. So we're breaking away from that triangular earth pressure where the bottom layers of reinforcement have the highest load. And then that empirical ratio, stress ratio, that Kr over Ka is now replaced by some stiffness terms. So there's a global stiffness factor and a facing stiffness factor and a local stiffness factor. And we'll go into those. So these are much more involved in determining these factors than our simple Kr over Ka. So in the simplified method, first, at any reinforcement level, we don't determine the vertical stress. We determine the vertical stress at the bottom of the wall. We multiply that by the active earth pressure, not a Kr over Ka pressure. And then that vertical stress is distributed vertically within the wall with this dt max function. And I won't go into the equation in any detail, but this figure shows that as we go down from the top of the wall at a depth of 0.6 times the height, at that point, our load and the reinforcement is uniform to the bottom of the wall. All right, so we don't have that continuing to increase with depth that we have for the simplified method. The equation is actually quite similar to the simplified method for Tmax. We have our vertical spacing here, we have our load factor for the vertical earth, we have the total height of the wall now times its weight times that dt max term, right? So that, and then we have our surcharge, and here we're going to modify that based on the height of the actual height of the wall versus the reference height of 20 feet, which is empirically where a significant portion of the data was obtained. And then we're going to have our live load surcharge. Then it's times K now, not Kr over Ka, times this empirically influence factor that captures the soil reinforcement properties and the wall geometry. And that term is, these three terms are facing stiffness, our global, and our local stiffness. Right? And so our facing stiffness is a function of the global stiffness of the reinforcement and this F sub F factor. And if we look at that factor, there are a lot of terms in it, but the one I really want to focus in on is this B. So this term F sub F is a function of the thickness of the facing column cubed, right? So if we have a 1 foot thick unit versus a 2, well, that would be 8. So you would reduce this number, would be an 1/8 of a 1 foot. And so this number gets smaller, and so the load and the reinforcement gets smaller. So there's a very large impact on that based on the facing stiffness. The global stiffness is the stiffness of all the layers of reinforcement added together, and it's based on the secant tensile stiffness of the material at a 2% strain over a 1,000-hour duration. So that information is not always readily available, but the National Transportation and Product Evaluation Program, NETTEP, many of the geosynthetic manufacturers have submitted their materials for that. And within that document, this secant tensile stiffness is provided. So that's the overall stiffness. And then at any reinforcement layer, we're going to have a local stiffness. So that'll be the stiffness of that one layer of reinforcement times its vertical space. So that's the simplified method to determine Tmax. Now, the simplified method is based on the fact that soil failure, we want to check and make sure that we're in the service state, that we don't have soil failure. So we have a second check to make sure that the strain in the reinforcement does not exceed a strain of 2 to 2.5%, depending on the stiffness of the facing system, whether it's a flexible facing or a stiffer facing. So we have to go and do this analysis all over again, but with service state. And so our load factors are going to change. So our vertical load factor for the ultimate is 1.35. Here we're going to use, and again, this is empirically derived, 1.2. And for the live load surcharge for ultimate, it's 1.75. We're going to use 1. So we redo the analysis to determine this Tmax for soil failure. And then we want to check the strain in that based on Tmax, and it's got to be less than 2 or 2.5% for a flexible face system. So, so my little summary of the simplified method, it's not really simple, but it provides significant benefit for the added mass when using large modular block wall units. There's no other design that directly incorporates the benefits of the large mass there at the face. And the additional benefit is that below a depth of 0.6 times the height of the wall, the vertical stress no longer increases linearly with depth. All right, so that's the simplified, as simplified as I could make it in the presentation. Now the last is our limit equilibrium method. And while this method certainly has been around for a long time, its implementation into MSE walls is relatively new. We use it for external and compound, or global and compound stability, but we haven't traditionally designed our walls using limit equilibrium. And so if we look at the diagram on the left here, which is, we're going to do our analysis from the top of the wall down. So we're at the first layer of reinforcement is here, and the second layer of reinforcement is right here. So we're going to look at failures that would cross only the top layer of reinforcement. And if we did a bunch of searches, we'd find that at a relatively steep failure surface, we'd have some required load to get that to a factor of safety of 1.5. At a different one, the load would change. And so we could create for all these different failure surfaces a required strength envelope. And now if we continue that process and we go down now to the third layer, so now we're going to intercept 2 layers of reinforcement. For each failure surface that we analyze, the T that's required to get that to a factor of safety of 1.5 is divided and split evenly between the 2 layers of reinforcement. And so we can now create, just like we did for the first failure for 1 layer, we can create the required strength envelope for the condition where we're failing just above the 3rd layer of reinforcement. And then it's a little complicated, but if this is the strength envelope for the failure for layer 1 only, and this was for layer 1 and 2, you can create this composite required envelope of strength. And so you continue this process down to the full height of the wall. And once you've done that, you've created what is your required strength envelope for that reinforcement. And it's going to be a function of the pullout capacity at the tail end, and the connection at the face of the wall here. So we've got a connection strength, and then we develop pullout, and then we get to some required design strength, and then it decreases. So by using this method, we can now determine what is the required strength to provide a factor of safety of 1.5. But to provide a factor of safety of 1, we're then gonna, so we have to back calculate. So limit equilibrium doesn't satisfy LRFD. The design strength envelope determined above should be determined at a factor of safety of 1.5. And then the envelope should be, the design strength envelope should be based on the allowable connection strength, the reinforcement, and pullout strengths. So we actually are going to use factors of safety for grids or strips based on rupture and of 1.7 and 2.4, and then for pullout 1.9. And these are a function of the load and resistance factors that are used for our requirements for our simplified method and our simplified stiffness method. So the limit equilibrium analysis summary, there's no direct benefit of the large mass of the large modular block units in the analysis. It actually, this method of analysis, there is less stress at the connection, and so the benefits of large blocks with full connection capacity isn't realized. The distribution is more uniform with depth than the simplified method, so that's certainly a benefit. And then I have just one kind of simple example. I took a 30-foot high wall with 30-foot high wall with a large block. I've used a block that's 2 by 2, right? So my vertical reinforcement spacing is 2 feet. I'm using 100% coverage of the reinforcement, so it's continuous at each level. And I've used friction angle of 34 degrees for the reinforced and 30 for the retained and foundation soil. So, so this is reinforcement levels, right, with depth from the top of the wall down. And this is the T-max that we've calculated for the different methods. So if we first, let's just look at our simplified method. So that's, you can see it increases with depth because it's a triangular earth pressure distribution. And the total force required for stability is 23.1 kips per foot. For the simplified method, or for the limit equilibrium method, now we determined what was the required strength and the reinforcement based on the example that I just showed. Then what we do next is we then run the analysis, inputting our materials that we're going to use and search for failure surfaces internal to the structure. So ones that just are between the tail end of the reinforcement and the face. And for this example, you'll see that the upper layers of grid, the failure surface fails behind those. So this was the critical factor of safety of 1.5. If I back up, that's why we see some zeros in the force here. But the total force for stability with a factor of safety of 1.5 is very close to the simplified method. What those guys did a pretty good job back in the day, didn't they? And then if we look at the simplified stiffness method, remember I used a 2x2 block, so that had a big impact on facing stiffness. But you can see that the loads are approximately a fourth of the loads of the other two methods. So here, clearly a huge benefit in the need for reinforcement within this simplified stiffness method. So I think I'm just about right on time, and I'm gonna try to transfer to Daniel, if I can.
Jim, are you saying
I transferred Daniel? Yes, we are. Success.
All right. But there it is. Are you saying the presentation mode?
No, Daniel, it is not
Oh.
yet. It's up in the top left-hand corner.
But is it in presentation mode? No. Hmm. Now?
Yes.
Okay, thank you. Sorry about that. Good morning, good afternoon to everybody. I'm Daniel Alzamora, and I'm with the Federal Highway Administration. I'm one of the senior geotechnical engineers with the Resource Center. And my job today is to explain a little bit about the IDEA evaluation of wall systems. I'm just going to tie into what Ryan and Jim have already talked about. So a little bit of history. The MSE walls have been around for a while, and we've been using evaluation programs in the past. But in 2014, we, the FHWA, decided to take a look at this again and relook at how we are doing these evaluations and what the evaluations we're doing with the systems. So we are looking at technical evaluations of retaining systems and their components, and we are looking at how we warehouse and maintain these evaluation reports for public consumption. So in the past, we were using what was called the high-tech evaluation program, and now this new program, the IDEA program, has replaced the high-tech evaluation program. And we have partnered, the FHWA has partnered with the Geo Institute, the ASCE Geo Institute, to manage this program. And if you go to this website, you can access all the information that's available about the IDEA program at that website. If you forget about this website, you could just go to the Geo Institute's website and go to special projects and then click IDEA. You could probably just Google IDEA Geo Institute and you'll pull this right up as well. But again, so why did we move from the high-tech evaluation program to IDEA? The high-tech evaluation program was developed in the mid to late 1990s, around that time frame. And it was at the time when MSE walls were just beginning to get introduced to the state departments of transportation. And there was a lot of different systems out there, and state DOTs were hesitant in implementing them, primarily because they weren't sure how these systems worked. They didn't understand exactly how they worked. They weren't used to seeing this small facing with these strips or geosynthetics to reinforce the soils. So there was a need to take a look at this a little bit more carefully and evaluate different systems thoroughly in order for the state DOTs to feel comfortable in implementing them in their projects. So, but since then, you know, the systems have evolved, but the high-tech evaluation program hadn't. So some of the issues and challenges that high-tech suffered were that it was not a very well-funded program. It was not well resourced. The time it took to get these evaluations done was very long. In many cases, taking 12 months. In some cases, taking longer than that. There are some quality issues. There was some misuse of these reports by owners, the state DOTs, the designers and suppliers. There was no way to maintain these evaluations. So an evaluation that was developed and done in 1998, it would still be the current evaluation of that system, of that named system, even though in some cases those systems may not, the components and the connections and the system itself may not reflect what was originally evaluated in 1998, let's say. So there were some issues with that. And there was no way to warehouse these reports. The only way you can get one of these high-tech reports were in hard copy. There were no PDF files. There was no online maintenance or availability of these reports. So you could either get it from a supplier that gave you a hard copy, or you can go to ASCE and purchase a report from them. And that was the only other way to get those reports. So those were some of the issues that we wanted to address. So we first needed to revise the premise of MSE walls. MSE walls now 30, 40 years, 50 years in practice here in the US and worldwide. We needed to think that this is not a new technology anymore. It's a mature technology. We have well-established design and construction guidance by FHWA and AASHTO. And just about every state DOT uses MSE walls as their standard of practice for most embankment construction out there. So this is not a new technology. We are not trying to address the issue is what is an MSE wall? How do these strips and geosynthetic reinforcements support this 6-inch spacing? We are way beyond that, way of thinking. We are in a situation where this is a mature technology. So the program, we wanted to make sure it looked at MSE walls, gravity modular walls, as well as other earth heating systems. We wanted to allow and encourage through this evaluation program some innovation of these systems and maintenance of these evaluations by making it easier to do once you have a full evaluation of your system and you make one small change to the type of reinforcements that you're using, or the facing connection changes slightly, you could submit those changes to IDEA and make those adjustments to your evaluations without having to go through the full process, which means that it becomes much more efficient to do these, and encourages you as a supplier to make these innovations and make these changes, because you understand it's not going to be a huge issue to make to take advantage of those in the future. And our intent is to make this a much faster, being, I believe our goal is to do these reports, these full evaluation reports, in about 12 weeks, and make them much less expensive to process than high tech. So that's what the program is intending to do. In this presentation, I'm going to give you an overview of what this is and what this evaluation protocols are. But if you want some additional information, there are 3 webinars that we put together last year, in the fall of last year, to go over these protocols in much more detail. And if you just go to the Geo Institute's YouTube page, you'll be able to find them. If you just Google IDEA tutorials, Geo Institute, you'll also find them. Anyway, there's 3 webinars. Each of them are about an hour long. You can scan through them and find information that and get some questions answered. There's some Q&A at each one of these tutorials, so it's a good opportunity for you to learn a little bit more about this program. And since I have these pictures up on this slide, I took the and we are not sharing videos in this presentation. Took advantage of letting you know who we are. This is Ryan, and this is Jim. This is me, Daniel, and the other 2 speakers are Silas Nichols and Jeff Greenwald. Silas is the principal geotechnical engineer at FHWA. He's located in our DC headquarters office, and Jeff Greenwald is managing the IDEA program for the Geo Institute. So that's just who we are. I just thought I'd take advantage of this slide for this. So what are the benefits of IDEA? And these are benefits, as I see them, for not only the state DOTs or the owners of these retaining walls, but also the suppliers who are trying to get these systems approved by various owners. They are independent evaluation of MSE wall systems. So it's a way, as I like to say, to communicate the work that the private sector is doing to these public sector owners, because we don't have a good way to communicate directly or accept this type of information directly without a way to evaluate the information that's being presented. So having this process or these protocols that are independent evaluations of the work that the private sector is doing is an excellent way for us to communicate. it accesses a wide range of experts to address system-specific items. At state DOTs, they don't have the expertise necessarily to look at corrosion issues or polymer chemistry and creep testing and pull-out testing and durability issues. So this allows, through the IDEA program, to access different people who have different types of expertise who can provide their input to the work that's being done with these materials and designs. It's a consistent evaluation report and submittals. So when you submit a system, you have a consistent practice of how these reports are submitted and then assembled as a final report. So every time for every single product or system, you'll have a very similar format for every single case. So it makes it a lot easier to go and find the different aspects that are of interest or things of concern that somebody might have, and it makes it easier for people to submit these systems for review because it's a consistent practice, consistent approach. It has some flexibility to accommodate changes in guidance, requirements by states, as well as new technologies. So as I mentioned earlier, it gives you the opportunity as a system supplier, if there are changes in guidance, design requirements, or you want to invent something new or create a new type of connection system between the reinforcements and your facing elements, you have the ability to first do all obviously do all the research and all of the testing that's required for you to feel comfortable with the new technologies, and then be able to submit all that research and all that work that you've done through the IDEA program for this independent evaluation of that work, so that the state DOTs can consider it in their approval process. It's a single location for state requirements and evaluations. So, and I'm going to talk a little bit more about this here in a minute, but in this IDEA, the IDEA protocols are, fairly encompass pretty much everything that you need. But each state DOT, you're probably more aware of it than most if you're in the business of trying to get your systems approved. Every state DOT is different, and they are all have their own particularities and requirements. And it's difficult to make one system that is acceptable everywhere. So there's always going to be some differences that need to be addressed. So we're working on putting together the requirements for each state DOT in one location. And I'm going to talk a little bit more detail in a minute about that. Information is readily available online and it's free of charge. So as I mentioned before, high tech, it was very difficult to get a report. You'd get it, like I said, from a supplier, or you'd have to get it from ASCE, and it would always be hard copy. These reports are all going to be online. They're going to be free of charge. You can just log on to or access the Geo Institute's website and download any of these reports. And you can direct your clients or state DOTs can go to this website anytime and download any of these reports anytime. So that makes it a lot more available, easier to access and distribute, and you have a place that you can direct people to get the report that was developed for a given system. They're up to date and current. So we want to make sure that we don't have this issue of a system that was evaluated 30 years ago and doesn't resemble what is being supplied currently. So we want to make sure that that is addressed. And we want to make sure that these evaluations don't take a lot of time and don't cost too much. We want to make it easy and accessible for everyone. So what is an idea evaluation? First, I want to say what it is not. It is not an approval, and it is not a certification. It is an evaluation of a given system. We are not developing research documents here. We are summarizing the work that's being done by system suppliers and providing an independent evaluation of the work that's been documented by the people who are developing these systems. So again, we want to encourage innovations, and we want to make sure that all of these this work is being well communicated and evaluated so that it can be processed. So then at the end of the day, we, the Federal Highway Administration or the Geo Institute, can't really approve a system. We don't do that. This is not our role. Each state DOT is their own entity, and they are responsible for developing how to approve a given system, or how they want to manage different products on their state systems. So they are responsible to review the evaluation reports and consider them in the approval of the systems. So the idea evaluation is only a part of the approval process, but it should address most of the requirements that are required by the state DOTs. So as I mentioned earlier, our current practice is, before IDEA, I guess I shouldn't say current practice because high tech is no longer anymore. I should adjust this slide. But what we have been doing in the past is there was no consistent process for evaluating the systems. The use of there was use of existing high-tech reports as part of the approval decision, but as I mentioned before, the high-tech evaluation reports were not necessarily updated or managed in a way to maintain them to be current. Some state DOTs required consultant evaluations of systems. So they'd have a pre-approved list of consultants that you can go to and get an evaluation of a system for that given state based on their requirements. So, and you might have to do that for many different states. So in some states, the in-house staff would do the evaluations. But again, there was issues always of having first of all, having the resources and the people and the time to do this work, and having the expertise to evaluate some of the work, some of the testing that you need to look at when evaluating these systems. Some states already include IDEA in their requirements with or without supplemental information and evaluations. And some of them have approved product lists or pre-qualified products lists and so on. So there's a wide range of practice out there. And the issues that we see are system evaluations from state to state are inconsistent. So just because you have it accepted in Arizona doesn't mean that you'll have a system approved in Nevada, because each state is very different. Evaluation of system require significant in-house resources. So it takes a lot of time for people to evaluate and review the submittals. They may or may not have the in-house expertise to conduct these evaluations. Like I mentioned earlier, require evaluations to be conducted by an approved consultant. Existing evaluations may be dated and not reflect what's being constructed, and difficult to implement changes to approved systems. So that's again the issue of if you need a new high-tech evaluation, you're not going to want to be, you're not encouraged or incentivized to make any changes to your system, because if you make any changes to your system, then what you're supplying is not what was evaluated. So that could be an issue, and it doesn't encourage innovation. So what we envision with IDEA is for DOTs and owners to incorporate and accept IDEA as a tool for system approval, so that what we would like to see is the state DOTs incorporate IDEA in their specifications as what might address most of their requirements, and then they may end up having some additional supplemental information above and beyond what is in the IDEA protocols. And we would like to see the state DOTs modify what their current approval requirements are to include an IDEA evaluation, and then outline what those supplemental information that's needed. And we're working on that right now, as far as from the Geo Institute and Federal Highways. We're trying to develop a way for anybody to see what are the requirements at any given state. So we started this maybe a couple of years ago, and the blue states and the green states here are states that we've already reviewed their requirements and have uploaded those informations onto the Geo Institute's website. And I'm going to talk about that here in a minute. The yellow and orange states we're in the process of developing. So currently there are 16 state reports on the Geo Institute website, and I'd say by the fall of this year, we'll have all state DOTs and territories the requirements for all state DOTs and territories available online at the Geo Institute's website. So you'll be able to go and see if you want to get your system approved in Missouri, for example, what you need to do and where you need to find the information to submit a system approval for Missouri or any other state. So here's what we've put together. So here's the website, and if you go to click on this button here for additional DOT system approval requirements, you'll pull up the list of states that we've completed these reports, and it has the date of when those reports were completed, and you can click on any of them or all of them and download whichever one of these you want. And I will say one thing on these, like I've mentioned already, every state DOT is very different. So some states have a one-page report, and there's a few states that have significantly more requirements than others. Now, what's online here and what we've developed in these reports is not creating new requirements. It is just documenting what the requirements currently are for each one of these state DOTs. So just wanted to point that out when you're going through some of these. Some are fairly straightforward, some are much more involved, but you probably already know that if you're in the business of getting these systems approved. So I want to take the opportunity to just show you 3 examples, and I picked Indiana, Tennessee, and Vermont as examples. And I wanted to just review what's in the reports that we put together. So here's what's in Indiana. This one is a 3-page document, and it tells you that where you can go in and find the information directly from the state. So we want to make sure that if you want to, you can obviously take a look at what's in here. But if you want to go look at specifically from the state DOT where that information is, you have that information. We want to make sure that the Indiana DOT is aware that they can make changes to these to what's in these reports. So if the state makes some changes to the requirements, we are hoping that they go in or they send us the information of their changes so that we can make an update, keep this information updated. And there'll be a version and a date for that, for these reports. It says in this report that Indiana accepts IDEA reports as a vendor approval request submittal. So they will take a look at IDEA as part of their submittal requirements, in addition to some additional information, which is listed below. And I'm not going to go into the details of what the requirements are here. I'm just trying to, and I'm not expecting you to read this information. All I wanted to do in these slides was to give you an idea of what's in these reports, just generally. So the submittal requirements are, and the Indiana DOT has two types of, or has broken this out into two different areas. One is if your system has been approved in a different state, you can go to this part of it. And if your system has not been approved in a different state, then you have to, in addition to these requirements, you have to add the steps 8 through 12. So that's what's in this report. And again, I'm not going to go into the specific details of what's in here. I encourage you to go into the Geo Institute's webpage, download a couple of these, and take a look at what each state DOT requires for their review and approval. And then don't forget that there is a version and date and version number for each one of these reports. Then Vermont and Tennessee, again, where the information is at the state DOT, talks about IDEA evaluation is accepted and with some additional information, and gives you what additional information is required, which is these 4 items in Vermont. So again, it's very different than what it's in Indiana. In Tennessee, they list the types of wall systems that are in their list. And Tennessee accepts the IDEA report as a vendor detail submittal for the proprietary gravity wall systems and MSC wall systems. And in this particular case, there are no additional items listed to supplement an IDEA report. So if you have an IDEA report, you can just submit it to Tennessee for their consideration to be included or added to their approved products list. They, of course, reserve the right to ask for additional information if they feel necessary. Okay, but generally speaking, they take the IDEA evaluation as the information that they need to consider you in their approved products list. The other side of the equation is, as a system supplier, where your reports are and what information is in those reports. So if you click on the evaluation reports, there are currently 7 reports that have been uploaded, and there are probably others in review and others coming in the future. Jim can probably address that during the Q&A. I guess that'll be a question for me, for Jim, so he can prepare. But he can let us know how many other systems are in the queue and in the process. And I thought I'd take one system and just take a look at the report that system put together, and talk a little bit about that as well. So the full report, so if you click on that button and then click on download that file, you'll see that that PDF file is 853 pages long, okay? But the first 5 pages are essentially the evaluation reports, basically like your executive summary of what's contained in this report, and probably what most people will read, right? They're not going to read 853 pages. And it includes what was submitted by the supplier for transparency. So everything that was submitted and was used to evaluate the system is included in this report. So in this particular report, it happens to be an update to a high-tech evaluation that was conducted in 2010. So it's a 12-year-old report that is now a current report. So now it's a current IDEA report that has a high-tech evaluation attached to it. But the IDEA evaluation is the one that supersedes the high-tech. But it maintains that history of that particular system. It outlines that there are no outstanding issues and that an owner can use this information to consider the system in their evaluation for approval. It outlines what type of checklist and what protocols it was used to evaluate the system, and it also talks about part of what we were trying to do, and we recognize that there's some proprietary nature and some confidential information that could be submitted through this process that the system suppliers may not want to have out there. So we allowed that for system suppliers to say we don't want part of this information reported, but we wanted to make sure that those kind of things were noted in the report because we wanted to make sure everything was transparent. So in this particular case, there was nothing that the applicant considered confidential. So everything that was submitted is in this report. Then the report goes into the different components, the system history, properties. It talks about the different parameters that the system that you would use in order to use this system with different materials and different reinforcements. And again, we're using the National Product Evaluation NetPEP, which is an AASHTO-based evaluation of geosynthetics to document the material properties of the geosynthetics. We are not doing any testing as part of the IDEA evaluation. Then after those 5 pages, there's a 36-page product submittal that was submitted by the system, which talks of much more detail about the components, the design, the construction, quality control procedures, performance of the system, and whatever other information the system supplier thinks is important to be considered in this evaluation. And then after that is followed by these 812-page appendix that incorporates all of the product test reports, data interpretation, example calculations, drawings, aesthetics, construction manual, specifications, and everything else that they submitted for this evaluation. But it's a good way you have this executive summary, you have the more detailed information about the details of the system, and then all of the testing and that is available for that product, so that an owner, if if they have a particular question about a given system, about a given aspect of the system, they can go and easily find it. And these reports are going to be fairly consistent, so they'll know what sections to go into in order to access this particular area of interest fairly readily. So hopefully helps expedite and optimize this process. And part of that evaluation is talk about connections and the details, talks about reinforcement properties, the NetPEP report, and those details, as far as in addition to the design calculations that were submitted for that system. So obviously I'm not asking you to read this details, just give you some idea of what's in these reports, and hopefully encourage you to access these reports to get some additional information of what's available. So just in summary, and just to close up here, just in time, I think, there is a need to conduct these system evaluations. State DOTs are already requiring these system evaluations at different levels, and different states have different ways of doing that. So, but the process is currently state by state, and it's not very consistent. So each state DOT and system supplier spends a lot of time and resources and money to do these evaluations. So what we would like to see is a more streamlined and efficient process of this, and that's the intent of what we're trying to do with this IDEA program. To improve the ability to make changes and incorporate innovations to systems. We don't want to stay stagnant and just keep using the same thing over and over again. We want to take advantage of the innovation and the great work that the private sector does in developing new products and new ways to do things. So this is, I think, a really good way to incorporate those innovations that that you guys do or develop. And then we also want to make sure that the systems that are being supplied to the projects for construction are what has been approved by the state DOTs. So trying to balance innovations with some being able to evaluate those innovations before they get implemented into projects. So that's the end of my talk. Here's my contact information. If you have any questions about this or other aspects, just feel free to give me a call or send me an email. And I turn it back to you, Ashley.